Welcome to The Explainer. Today, we're skipping the fluff and diving straight into the very foundations of the physical universe. We're going to strip away all the complex jargon and revisit the absolute first principles of chemistry. I'm talking about the undeniable rules that govern literally everything you can touch, see, and interact with on a daily basis.
So let's kick things off with our first section, the science of transformation. When a lot of people hear the word chemistry, what immediately pops into their heads? Probably a static table of elements, rigid numbers, or maybe some really dry, dusty textbooks. But let's completely pivot that mindset right now. Chemistry is, at its absolute core, the study of molecular transformation. It's not a static list. It's the active, highly dynamic study of how matter actually changes its composition and its form. Whether you're digesting your breakfast, refining crude oil into gasoline, or simply frying an egg in a pan, chemistry is happening whenever and wherever matter changes. It really is the central science of transformation. Moving right along to Section 2, we need to lay down the ground rules for defining matter and space. Before we can even begin to understand how things transform, we have to define what those things actually are, right? So, what is matter? The strict first principle definition here is absolute. Matter is anything that occupies space, which means it has volume, and has mass. If it doesn't have both of those things, it simply isn't matter. Now, solids and liquids, they're pretty obvious. But think about a balloon. When it's empty, it's just fly, but you blow it up and it inflates. That gas inside is actually taking up physical space, and it has mass. That makes the gas definitively, undeniably matter. All right, into Section 3. Let's tackle a really common misconception: mass versus weight. We all do it. We use the words mass and weight interchangeably in our everyday lives. But in chemistry, they are vastly different concepts. Mass is the intrinsic, constant amount of matter in a given object. It's what you're actually made of. Weight, on the other hand, is merely the external force that gravity exerts on that mass. Here's a fun fact to put that into perspective. Because gravity is actually slightly weaker the further you get from Earth's center, you technically weigh slightly less at the peak of Mount Everest than you do down at sea level. But your mass? Your mass hasn't changed one single bit. Picture an astronaut traveling to the moon. Her mass remains exactly the same on the lunar surface as it was back home. But because the moon's gravity is so much weaker, her weight drops to just 1/6 of what it was on Earth. So how do we handle this in the lab? Chemists use a highly precise tool called an analytical balance. By comparing an object to a known standard mass, we can figure out exactly how much matter is present, completely independent of whatever local gravity is doing. It's a true measurement of the material itself. Next up is Section 4, the states of matter. This is where we start zooming in. Let's start with the macroscopic reality, the stuff we can see right in front of us. A solid is rigid, right? It possesses a definite fixed shape and a fixed volume. You put a rock in a flask, it stays a rock. A liquid is a bit different. It flows to take the shape of its container. It'll form a flat or maybe slightly curved upper surface because of gravity, but its total volume still remains perfectly fixed. A gas, though, is highly adaptable. A gas will expand to completely fill both the shape and the entire volume of whatever container you put it in. But why exactly do they behave this way? Well, it all boils down to kinetic molecular theory. Think of it like this. In a solid, the molecules are tightly packed together in regular patterns. They're just vibrating in fixed positions, kind of shivering in place. Now add some thermal energy and they transform into a liquid. The particles are still touching, but now they have enough kinetic energy to sort of slide and tumble past one another. That's why liquids flow. Add even more energy, and boom, they become a gas. The attractive forces holding them together are completely overcome, and the particles just fly apart, moving rapidly and independently. Ultimately, phase changes are just a constant tug-of-war between attractive forces pulling things together and kinetic energy pushing them apart. Which brings us to our final part, Section 5, the bridge to organic synthesis. So we've explored matter, we've looked at mass, and we've talked about kinetic energy. But you might be wondering, so what? Why does this actually matter to us in a real practical setting? Why do these basic phase changes, just knowing about solids, liquids, and gases, matter for something as complicated as advanced organic synthesis? It might seem incredibly elementary, but trust me, it is the absolute bedrock of high-level laboratory work. Think about advanced organic chemistry.
You run a reaction, and your desired, highly valuable product is suddenly mixed into this messy soup of liquids and other random chemicals. How do you get it out? You manipulate the states of matter. You deliberately adjust the conditions, the temperature or the solvents, so that your specific product transforms from being completely dissolved into forming a solid crystal. We call that a precipitate. By forcing this exact phase change, you can physically filter that solid right out of the liquid, isolating your perfectly pure product. Every single complex synthesis relies on these exact first principles. So the next time you hear about a groundbreaking new life-saving medication, ask yourself, isn't it incredible that the entire process ultimately relied on simply knowing how to turn a liquid back into a solid?